All right, so circular motion. First of all, let's talk about linear motion. I know that sounds like a bit of a backtrack, but linear motion, that's just that old-fashioned type way of talking about motion, just moving back and forth along one axis. Okay, so when we first talked about linear motion, one of the very first things we talked about was speed. So delta d over delta t, and that was a long time ago that we talked about that. And we pretty much defined speed using this equation, and you know, it hasn't changed. It's the same. The nice thing is that this equation also relates to circular motion with a little bit of a twist. We just have to remember how we're moving. So I want to draw a little diagram off to the side here. Remember, if you're going in a circular path, you're going all the way around in a circle like that, right? That's the pathway. And so I might talk about this as a trip around the circle where there's a property of this circle that we call r, which stands for radius. Yeah. And if you know the radius, what can you tell me about the distance around that circle? Yeah, we say 2 pi r. Yeah. 2 pi r is the circumference equation, right? Now, if I want to relate the idea of circumference to this idea of distance, could you wrap your head around the idea that the distance around a circle is its circumference? Okay, so no problem. If I want to talk about circular speeds, then, I would be talking about 2 pi r as the distance around the circle one time. That makes sense. Now this is going back to your knowledge from sound and waves. When you have a cyclic motion, because if you go around in a circle, you know that that's a cyclic motion, right? So we're going to borrow vocabulary from sound and waves. What's the name for the time that is measured when you talk about one full cycle for a wave? Do you remember?
Period.
Yeah, period. Period. So if I talk about the delta t for one cycle, I'm making up notation here, delta t for one cycle is what we call the period. But you know, 2 pi r is only one trip around. It's the circumference, one trip. So people say 2 pi r divided by period is the speed. That's the average speed for that trip around the circle. So we can label up our terms here. We can say r is for radius, t is for period, which wouldn't stand up on Sesame Street because t doesn't really stand for period, but it represents period, okay? So we've got a period there. Remember, this is just an exclamation mark type of statement. Do not use lowercase t and uppercase t interchangeably. And as I look through people's notes and sort of look over your shoulders and things, people use these guys interchangeably. It really matters. Uppercase t and lowercase t are two very different things. Treat them as two totally different letters in this circumstance. Capital T, obviously, in another circumstance, could mean temperature. But in this situation, lowercase t is total amount of elapsed time, whereas period is specifically how much time it takes for one cycle. Has everybody sort of got that? It's a big difference. Because I could go around the circle like 10 times, and I'd get a certain amount of time. How would I get the period if I went around the circle 10 times, though? Yeah? Yeah, divide that time by 10. Perfect. So let's throw that down, because that's another related equation that we may use at another time. We might say that period is equal to, is it delta t over n, or n over delta t? Delta t over n. And again, it's always useful to be able to fall back on the units and say, what makes sense here? If I have seconds as the units on top divided by some count, it makes sense that I'm going to get seconds coming out the back end of this thing. And the same thing with circular speed. If I have 2 pi r, the only contributor to units here is the r, meters. And the only contributor down on the bottom is period, seconds, meters per second. So the units work out for the centripetal, or sorry, not centripetal, I'm using the wrong word, circular speed, okay? So both of those guys are good equations for our circular motion. Now, on the flip side, if I want to define frequency, which I really am not looking for right now, it's 1 over the period, but hey, maybe if you're told the frequency for an oscillation, you could go back and use the period, or find the period that way. So I'll throw it out there, just as an in case you need to know, or as an in case you need to be reminded. Let's go on from there. I almost want to say derive equations, but I want to figure out where a couple of equations come from. So I want to label this next bit centripetal acceleration. Centripetal acceleration. And in the past, we've said that acceleration is equal to delta V over delta T. That was for linear scenarios. And I just want to throw this equation out there. I would like to claim that acceleration for circular motion could be stated as circular speed squared over r. And I'm not going to go into the nitty-gritty of where that came from. Okay, not at this time. I will call it equation 1. And off to the side, I mean, if you want to get into it and we want to talk about some of your calculus and vectors background, off to the side afterwards, we can do that, but I can't assume that everybody's got that background. So I'm just not going to go into that aside about where that equation came from right now. It's just mathematical for us, okay?
So that's a C, is that confusing?
It is a C, yeah. Circular speed. But I do want to remind us of an equation that we just sort of came up with. It was VC equals 2 pi r over the period. I'm going to block that off because I want to talk about what would happen if I subbed equation 2 into equation 1. End up getting AC equals, instead of saying VC squared, I'm going to write 2 pi r over period times 2 pi r over period all over r. And if you don't like that notation, that's okay. I don't care. It ends up, if I multiply across the numerator, I get 4 pi squared r squared all over period squared. You know, we're just multiplying across the numerator and the denominator. And all of that is over r. Now, if you want to simplify this, you have to recognize, hey, look, this is actually r over 1, so we have this fraction divided by this fraction. So when you divide a fraction by another fraction, you invert and multiply. So I'm running out of space here. So I would come back up to the top and I'd say, well, centripetal acceleration then is equal to 4 pi squared r squared over period squared times, not r over 1, but flipping it, inverting and multiplying 1 over r. Then I get to do some simplification. R, gone. R. Pirate mathematics. And we end up getting 4 pi squared r over a period squared. And there's no more simplification that can be done, so I'd like to call that equation 3. And again, I'd like to point out, I think I'd like to do this as just a quick aside. I want to point out that the units work out. So you don't have to write this, but I just want to show you. Do you see that red line on the screen? Let's make sure the units work out. So VC is in units of meters per second. And that's squared, so times meters per second. And all that is divided by meters, which is the same as saying meters squared per second squared, times, and again it's invert and multiply, times 1 over m, cancel, cancel, equals meters per second squared. So even though this is centripetal acceleration, the units do work out. Oh, I chopped it off, sorry. The units do work out. And we could do the same thing for this one. R is in meters, period is in seconds. Meters per second, speed, no problem. We could do the same thing for this guy down here. R is in meters, period is in seconds, but seconds is squared, and pi doesn't contribute any units, so it's meters per second squared. So people get hung up on, oh, are the units all going to work out? We're going in circles now. Is it different somehow? Well, yeah, it's different because we're going in a circle. But yes, it's the same, and the units are all going to work out for us. Okay, so don't get hung up on units being different. All we have here is, well, the only thing that I really brought up without a full explanation is this equation, so I'm asking you to take it on faith. But after that, it's really just a little bit of substitution and rearrangement. Does anybody have any questions at that point? Yeah?
Because it's circular, we don't have to worry about like the little vectors and the acceleration.
Oh, good point. If we wanted to be most correct about this, we could put an arrow above all these guys. But in just a second, I want to talk to you about what happens with the direction. Okay, so you can't have curved vectors.
Yes.
No. In this context, that doesn't make any sense to us. Okay, so let's see what happens with the direction. Okay, and it follows the same rules as we talked about before. So again, we're just talking about a new situation here. We're not introducing new rules or anything.
Okay.
It's just a new situation, which is kind of comforting. It means that you've seen the rules before. Right? You're just dealing with it a little bit differently. So let's talk about vector analysis. Oh, that marker's dying on me. Vector analysis of, let's just call it AC, centripetal acceleration. And just for fun, I'll put the arrow on top of it. So to start out the conversation, I think it would probably be a good idea to draw a circle. So here we go. See if we can do it. Here's the center. Need sound effects. Okay, there's the circle. Okay, and the circle's going, well, the motion of an object following this path. Let's call it an orbit, just for no other reason than it's shorter than saying circular path. So an object is following this orbit, and I'd like to propose that I want to think about its velocity at this point and its velocity at this point. And I just want to draw in vectors, okay? So the velocity at the first point, I'll call it point 1 in just a second, is v1. No numbers yet. The velocity at point 2 is v2. And I'd like to talk about how to calculate acceleration again, because we said before, centripetal acceleration is v2. Oh, sorry, we said before the acceleration was v2 minus v1. We haven't said this before. This is new. v2 minus v1 over delta t. And in vector analysis, that's true. v2 minus v1 is delta t. It's hard to just plug in numbers because this is a two-dimensional situation though. So v2 minus v1, we've talked about previously, brings up an issue in two dimensions. We have to redraw the vector diagram, right? So instead of saying v2 minus v1, I want to say v2 plus negative v1. We've done this before. And I want to draw what that looks like. v2, no problem. I'm just going to draw it underneath of this expression. v2 is downwards. Negative v1, well, v1 points to the right, so negative v1 must point to the left. And so if I want to show what this expression actually looks like when it gets added up, I'll just do it sort of as an equally typed arrow so that we can see that this is a picture that's going to represent this expression. It would look like this. Tip to tail addition says v2 goes down. Call it v2. Negative v1 goes over. We call it negative v1. And so there's a vector that's going to go from the beginning of the first one to the end of the second one. And what do you call v2 minus v1? What's the algebraic symbol for v2 minus v1? It can be, yeah, delta v. Wrapped up in one simple variable. That's delta v. Change in velocity. Delta v is kind of down at an angle like that. Now, if I want to add some values onto this, some actual numerical values, let's just say, make nice and simple round values, 5.00 meters per second and 5.00 meters per second. In other words, this orbit has an object going in a circular path where at two particular points in time the speed was 5 meters per second, but at one point in time it was 5 meters per second, to the right, and another point in time it was 5 meters per second down the page. Okay? Now if I wanted to find out what delta v is, you can see that just because I've chosen two convenient positions, I've chosen the 12 o'clock position on the clock and the 3 o'clock position on a clock. You know what I mean by that. These guys are, by definition, going to be at right angles to each other, and they're of the same length. So you could tell me that that's 45 degrees, so I'll just label that up just for fun right now. And you could also label up that as 90 degrees. Now I want you to do a little bit of Pythagorean theorem and find the magnitude of delta v, because it'll be equal to the magnitude of v2 squared plus the magnitude of v1 squared, all square rooted. Okay, and when I say magnitude, really and truly I should put absolute values brackets on these guys. So 5 meters per second squared plus 5 meters per second squared. 7 point something or other.
7.071067.
Okay, I'll stop it at 7.071, okay? 0.0711, you like that one?
Sure.
Okay, meters per second. Or approximately 7.07 meters per second. So we could say that there's a direction there, but I want to hold off on the direction just now. We haven't even gotten to the acceleration yet. I want to hold off on the direction just now, and I want to do a little aside, because there wasn't really enough information to figure out acceleration, centripetal acceleration in this. I'd have to tell you some more observations. So what if I told you that somebody sat here and counted the objects, or measured the amount of time it took for the object to do 10 orbits. So I'm going to make up some notation. I'm going to say delta t 10. That means 10 orbits. I'm just inventing notation, okay? But I'm telling you what it means. Delta t for 10 orbits, let's say that it was equal to 120.0 seconds. And so n would be equal to 10. What's the period on this guy? Can you do that math in your head? Period is equal to... Yeah. Period is equal to delta t over n, which in this case, 120 divided by 10. That shows nice round numbers, 12.00 seconds.
And you keep 2 places because the 10's absolute.
Yeah, the 10's a count, so it's infinite significant figures, if you like. Now, is that the delta t value up here, though? Think about what we just figured out. We just figured out the period. Is that this delta t? You got to go back to the picture. How do I get the amount of time it took to go around that part of the arc? Yes, ma'am? Divide by 4. It looks like it's a quarter rotation, so it makes sense that it would be a quarter of the period, so long as the speed stays constant, and I think that's a fair assumption in this case. So I could say period divided by 4, and if you like, we can call it equal to delta t, with no subscript of 10. 8, why not, eh? Is equal to, I'm going to run out of space on my page here, is equal to, so I'm going to just write the answer, not the substitution step. 12 divided by 4 is? 3. Well, I guess it would be 4 significant digits, but okay. 3 seconds, anyway. And now you could go back and you could do the calculation. Finally, we could at least get AC is equal to delta V over delta T, where delta V is equal to 7.07 meters. Oh, I should put in the unrounded value. 7.0711 meters per second. Sorry, that's messy. Divided by 3.000 meters per second. Knowing that we're going to end up having to round to 3 sig figs. What's 7.0711 meters per second? Oh, shucks. Seconds. Sorry, I saw somebody wince. 2.357? 57022. Stop it. Well, I'm going to have to go to 3 then if it's 604. Meters per second squared, because meters per second divided by seconds. Rounded to 3 sig figs, we get 2.36 meters per second squared. Okay, so we do have an acceleration. But what we don't have yet is a direction. We can see it's 45 degrees, but I'm not really sure what that means. This is a vector that has an angle, but where does it attach to the motion? How does it attach? What we've really found here is the average acceleration, because what we never really talked too much about, I guess we did, but acceleration average is equal to delta V over delta T. Well, okay, but where do I put this vector if it's the average acceleration? Doesn't it make sense that I'd put it in the average position? In between? It's the average acceleration. It should be in the average position. So the average acceleration happened right there, on average. And we're saying that it pointed, south 45 degrees west. Can you see that the centripetal acceleration points towards the center? When we see it in a vector diagram, it sort of makes sense because I've swung buckets around at the beach, and I know that the centripetal acceleration is kind of towards me because I can feel that tension in my arm as I swing the bucket around in the circle. But it makes sense in the picture here too. Does anybody have a question about why it points at the center? I'm trying to make an argument. What about this? What if this was v1, this is v2? What if I wanted to talk about what the average acceleration is between v2 and a new vector, v3? Let's just say for a second it takes the same amount of time to get from this position to this position because the circular speed isn't changing. So the delta t is still going to be 3 seconds. Let's take a look at the vector diagram again, okay? So off to the side over here, I'll say v3, well, delta v would be equal to v3 minus v2. v3 goes that way. v2 goes down, but minus v2 would go up. So v3 minus v2 looks like this. So delta v points up at an angle. Now, if that's the direction of delta v, it's also going to be the direction of acceleration. Remember, because delta v and acceleration are always in the same direction in these situations. And the average position between position 2 and position 3 is right here. So centripetal acceleration pointing up at an angle, again, makes the centripetal acceleration point towards the center. And you'll find the exact same thing if you choose a v3 and maybe a made-up v4 or something like that at each of the positions, 90 degrees around the clock face. You'll find each time that the vector points towards the center. Now, if you really want to get quite picky about it, and I do, you could draw a circle like this, and you could draw an instantaneous velocity that goes off like this. See, that's kind of not at the 12, the 3, 6, or 9 position on the clock face. It's in sort of a funny position. I could put another one here. Remember, it's at a tangent. And you could call this v1, and you could call this v2. And if I wanted to do v2 minus v1 this time, it would be, here's v2. Oh, I'm trying to make it right. That's not good. v2. v1 would go sort of up at an angle. See how that's the opposite of that v1? And I know this is kind of Mickey Mousey because I'm hand drawing it. But again, you get a delta v that points in that direction. And so at the midpoint between here and here, you get a delta v that points roughly in that direction towards the center. Okay, so it doesn't even matter. It doesn't have to be at these 12 o'clock, 6 o'clock, 3 o'clock, 9 o'clock positions. It could be any two random positions around the circle, and you're going to get the same result of centripetal acceleration pointing towards the center for these guys, okay, for a constant velocity, or constant speed, rather. The other thing is, what if can you see along this arc here, between v1 and v2? That arc there is much smaller than this arc here. Does it point any less towards the center? No, both towards the center. What if I made that arc even smaller, so that it was just off by just a little smidge, and you'd end up having two vectors that looked like, maybe I'll draw it one more time. This will be the last time. What if I had vectors that looked like this? Here's one tangent, here's another tangent. Don't you think if I drew this just perfectly, do you think I'd get the centripetal acceleration to point towards the center again? So in the limit where I shrink this tangent to be almost 0, you're going to end up, I said that was my last time, but I'll do it one more time. You're going to end up getting a picture that looks like vector 1 and vector 2 are practically on top of each other. It's going to look like one vector, right? Vector 1 and vector 2. And you'll still get a centripetal acceleration that points towards the center. And so people start talking about limits. And you guys have talked about limits in math class, right? Or you're going to soon if you haven't yet this semester. But if you how many people talked about it last semester? Limits. Okay, so one person took that course so far. So there's a thing called limits. In this case, in the limit where the amount of time between these two vectors approaches 0, that's how you write this down. In the limit where the time between vector 1 and vector 2 approaches 0, you're going to end up getting speed becoming approximately, now this is not proper notation, approximately perpendicular to the radius. Okay? Now that's not proper notation. But I want to make sure, does everybody get the idea? The amount of time between these two vectors is a little bit arbitrary. It could be a quarter of a clock turn around, a quarter of the period, or it could be just a fraction of a second. And if you could get the angles measured just perfectly on these two vectors, you're going to end up getting the radius perpendicular to the tangent of speed. And so people say that the centripetal acceleration is always perpendicular to the instantaneous circular velocity and points towards the center of a circular orbit. Cool? That's the argument, though. Okay? And we could get into more math stuff, but I am in a little bit of battle with where you might have been in your math courses or what you might have done in your math course. So how many people talked about limits before? 2 now. Okay, you're multiplying. All right.
Calculus, right?
Yeah, I think so. I think that's where they put it, right? Calculus? Yeah. All right. I haven't taught that course, right? So it's all hearsay to me. All right. So let's talk about driving cars. So my first period class said that they wanted to drive a car around a circular roundabout in London. Okay.
Wait, which London?
Ooh, mystery. Which London? Okay. I'm not going to answer that.
I'm not sure it's probably much more.
Yeah, there's probably more roundabouts in England. All right. So let's draw the diagram here. We'll call this part A. I haven't stated a question yet. We're going to drive around the roundabout. And I'd like to say that the roundabout has a radius R. And the radius of this roundabout is 12.0 meters. And you know, we might have some troubles with trying to figure out how fast this thing is going. Could you use? Is there a device you could use to figure out the speed of this car? Yeah, you could use a speedometer if you're in the car. Is there a way you could figure it out by being outside the car? Yeah, come with the speed radar. Why not, eh? We could definitely find out what the speed of the car is just by using a speed radar. And then another way to get around this would be to have somebody sit there with a stopwatch, right? You could figure out what. Yeah, keep on driving that race car, honey. And you know, if you used your stopwatch and you were able to figure out that the period for this car going around in a roundabout was 18 seconds, you'd probably be satisfied with yourself. Okay, so you wait for the car to go all the way around the loop, and as long as the car keeps on going around the loop, that's fine. 18 seconds. So let's make an assumption that it goes all the way around the loop once. If it does a half rotation around the loop, then you'd multiply whatever the time is by 2, because it only went halfway around. But in this case, we'll make the assumption that it went all the way around. I'd like to find the centripetal acceleration that the car is experiencing. Centripetal. Find the centripetal acceleration of the car. So you have enough information here to do it. Tell me what formula you'd like to use. I mean, this is really kind of like the equations of motion from kinematics, but now we're going in circles, right? So what's a nice, sweet little formula we could use? AC equals... Well, not 2 pi r over period.
4 pi squared r?
Yeah, 4 pi squared r. Over period squared. Alright, and we could sub in our values. Remember, never write 3.14 or even 3.14159 or some crazy thing like that. Just hit the pi button on your calculator, okay? You want to keep this as precise as possible. And somebody who has a good calculator and is quick on the buttons.
Go.
Yeah, where's Ferlin? Ferlin would have been on this question.
Yeah, we need Alex Ferlin.
I got it.
Where's the pi button in this calculator?
What did you get?
Second function.
Oh, no, I don't think so.
No,
I think it's closer to 1.5.
I'm pretty sure it's like a 1.4621636.45.
Yeah, 1.46. I'm going to go with 22.
I'm good with that.
All right. Meters per second. I'm glad. I'm happy if you're happy. So let's round this off to 3 sig figs. 1.46 meters per second squared. And again, if you want to, you can say towards the center And so this addresses your question about direction. Since the direction for the centripetal acceleration is always changing as the instantaneous velocity changes, it's kind of hard to say south. So we just say towards the center. We have to define that as a directional reference, just for the acceleration. Now I want to try a follow-up question here. Find the car's speed. Now, I really should be more specific. I should say average speed. Find the car's average speed. How could I find the car's average speed? What's a formula involving centripetal acceleration that you know? No, not delta V over delta T. Remember there was a nice equation that I gave you magically at the beginning there?
That 2 pi r over t.
No. 2 pi over period is the circular speed.
Oh, is that what you mean?
Oh, yeah, but I can't jump. Oh, you're right. What am I talking about? Here, I'm cooking this problem harder than I needed to. VC equals 2 pi r over a period. I could just jump in there.
Yeah.
Well, let's do that, and then I want to show you what I wanted to do, okay? Because I was all excited about combining equations and going to town on this puppy. All right, so 2 pi, I really wanted to make it happen. 2 pi times 12.0 meters. I just get excited. I want to tackle these problems and make them tricky for myself. Divided by 18.0 seconds. VC is equal to, what do you get?
$4.188.
Anybody want to second that motion?
Yeah.
Okay, motion carries. 4.188 meters per second. Now we could say approximately 4.19 meters per second. I want to show you what I was going to do because I got all jazzed up about this. I was thinking, what if I said, well, centripetal acceleration is the same as saying centripetal acceleration, eh?
Yes.
And centripetal acceleration is the same thing as saying v squared over r, right? And v squared over r is the same thing as saying centripetal acceleration. But centripetal acceleration is the same thing as saying 4 pi squared r over period squared.
That was not needed.
Can you see that I can get v now? Yeah. I don't know why I thought that was the direction I wanted to go in, but you can go that way. Isn't that kind of neat? If I cooked this problem a little bit different, where you didn't know the period, can you see that if I knew these values, the v and the r value, I could have gotten the period this way in the first place. I didn't even have to give you the period. I kind of got carried away and gave you too much information in the first place. Anyway, I just want to isolate this because I'd like you to see how it's done anyway, okay? So I've got my v squared. I'm going to take the r up to the other side, saying that 4 pi squared r squared over period squared. And since this is really v squared, I would square root both sides, and you get that. Now if I say that v is equal to 4 pi squared r squared over period squared, check out what happens. Each one of these guys is squared, isn't it? Couldn't I then square root the 4, square root the pi squared, square root the r, square root the period? Man.
Can we just like skip all that and just go to that?
What?
VC equals 2 pi r t?
Well, it's kind of the one thing is the nice thing about it is I might be able to go backwards and find the period value.
Okay. So
If you hadn't been given the
write
period
that
value.
down.
No, you just know that you can set equations equal to each other. It's really like solving by substitution, right? Can I tell you one more thing about this? Do you want to know the equation for centripetal force? Yeah, you should write this down. I'm going to put it in my margin, but you really should write this down. You ready for it? FC is equal to mass times centripetal acceleration. Ooh la la.
Almost. That's like the same as last year.
Isn't it?
But we just have C. So
Yeah, but doesn't that look just like Newton's second law?
yeah, that's what
Yeah.
Oh, okay.
Centripetal
Not
force.
going to.
Centripetal force is not a new equation. The only thing that's new about this is that we have a few new equations for centripetal acceleration. We could say v squared over r gets subbed in the AC spot, or we could say 4 pi squared r over period squared gets subbed into the AC spot. Either one works, okay? But the centripetal force equation isn't very fancy or new or anything like that, except that we recognize now we're working with circles, okay? So if I were to do this exact same question, and I told you, well, let's do it. Just for fun. Just for fun, let's say that a kitty is attached to a Newton spring scale. Okay, so don't do this at home. But if you attach a kitty to a Newton spring scale and you drive around in circles in roundabouts, you can give the kitty tuna and everything that kitties like. Hey, no fighting. You guys know this is being recorded, right?
Was that threat recorded?
Yes. Yes.
So if he ever actually hurts me physically, can I submit that to him to the courtroom?
Sure.
Yes.
And then also I will chirp you.
All right. Anyway, you chirp each other somewhere else. Let's go. Keep on. I know you guys are the best of friends, and there'll be hugs and handshakes afterwards. All right. So moving on, we got the radius of motion for this car going around in circles, 12 meters. We got a kitty cat attached to a Newton spring scale. What else we want to know here? Oh, what's the reading on the Newton spring scale? The kitty cat experiences. Well, let's see if we can make this kitty cat experience a different amount of force than he would have in the first scenario. We're going to change the scenario. The kitty cat experiences 17.0 newtons of force this time. Around. So this car is maybe going faster, maybe it's going slower. We're going to find out. So first I want you to find part I, find the AC the kitty is experiencing. Oh, I forgot to tell you the mass of the kitty. That's really important. The mass of the mass of the kitty is 4.5 kilograms. .50 kilograms. Now you can do it. Find the centripetal acceleration that the kitty is experiencing. I'm going to write out my solution here, and you write out your solution, and then between all of us, we'll know the answer. Isolating for AC. Before you sub in your values, and would anybody believe it's 3.78 meters per second squared? Okay. So approximately 3.78 meters per second squared. Oh, did anybody write down the unrounded value? That's what I didn't write down.
We a bunch of sevens in that
Oh.
3.7.
Okay. So 3.7 repeated meters per second squared. Okay. So then the next question that I might ask in a question like this, a problem like this, would be to find, oopsie.
If we just left it as 3.7 as we did and didn't write out 7777, is that?
Yeah, I'm okay with that.
Fine.
I'm okay with that. You can round it anyway, right? Yeah. So that's the problem with that. I use the arrow, the bar above numbers to represent repetition of a digit. as opposed to those people that put a bar above a number to represent significant figures, it can get confusing, right? So I'm going with repetition for the use of the bar. All right, so find the period of motion. Now, how would you like to find the period? What would be a nice method to get to that? Do you have an equation that would be useful? Yeah, Allie?
AC equals 4 I squared R over T squared.
Like that. Because we've got the R and we've got the AC now. So now we can isolate to get period all by itself. I could say period squared is equal to 4 pi squared R over AC. And then, really, I'm square rooting both sides here. So I get period squared. Oh, shucks. Period equals the square root of 4 pi squared times the R was equal to 12 meters. Oops. All divided by AC, which we said before was 3.7 repeated meters per second squared. And if there's anybody with a calculator, it's going to be close to 11. I like it. 11.198 seconds, or approximately, and I've just run out of space, about 11.2 seconds. And we could keep on going with this. There are a few more permutations we could do with this. But I think we get the idea of how to deal with the variables, okay? So I want to leave that there, and we'll call that all she wrote.